Instantaneous velocity and speed. Let's look at a position versus time graph, and let me go ahead and plot a continuous function. Here's some points that I plotted: A, B, C, D, E, and F. Here's the best fit curve in green. So in this position versus time graph, if we wanted to look at average velocity, all we would need to do is find the slope between any 2 points on this graph, and that would give us the average velocity. Instantaneous velocity, though, tells us what is the velocity at one point in time. So for example, let's say we wanted to know the instantaneous velocity at point A. Well, at point A, that would be the tangent at point A. The tangent in point A here is illustrated in red, and if I could find the slope of this red line by finding 2 new points on this red line and then finding the slope, that would give me the instantaneous velocity at point A. Notice that if I were to find the average velocity between points, say, A and D, let me go ahead and draw the line for those. The average velocity between points A and D, as you can see, is quite different than the instantaneous velocity at point A. Now, how do you find this instantaneous velocity? Well, the instantaneous velocity can be found by drawing a tangent line at that point and then finding the slope of that line by finding 2 new points on that line and then solving for slope. But you can also find it other ways. So that's what I want to talk with you about today. What are the other ways we can do this? Now, if we're talking about speed, instantaneous speed, where I'm really only interested in the magnitude or how fast you were going at that moment, you can just simply use a speedometer in a car. So if you're in a car and you look at the speedometer, that tells you your real-time speed or your instantaneous speed. And if you knew the direction you were going as well at that point, you could also write direction, and that would also give you then your velocity, because your velocity is your magnitude or how fast you are going and your direction. Well, what if we wanted to calculate this mathematically? Well, your velocity, when we are looking at a position versus time graph or a position versus time equation, mathematicians would say it's the limit of your displacement over your change in time as your change in time approaches 0. In other words, as you're looking at just one single moment in time. This can also be written as finding the derivative of your function at a particular time, and that can be written as a dx over dt, which means your derivative. It could also be written, if you're looking at x as a function of time, you would just have your x prime of t. So this is another way to write symbol for derivative. So how do you find a derivative? Well, there is a notation here that shows that if you have a x as a function of t, or position as a function of time, and it's equal to something that looks like this, the derivative, your dx dt, or your x prime of t, is simply going to be taking the exponent here, the n, bringing it over to the front, so I have n multiplied by capital A-T. And now the exponent that used to be t to the n is now t to the n minus 1. So this is how you write a derivative, or you do a derivative. Let's do just a couple examples on how to do a derivative. So in example 1, say you have position as a function of time using this equation. So you have a graph with a curve, and if you were to find the equation for that graph, let's say equal to this value here, and I asked you to find the velocity, the instantaneous velocity at some time. Well, first thing we would do is take the derivative, so we would find the x prime of t, and we would look at the first term here, and we would bring this 3 down to the front, so we would end up having 15 t squared plus. Now this next term, or 2t, there's that t has an exponent of 1. That 1 is brought down to the front, so I'm left with a 2. And then 1 minus 1 is just 0, so t to the 0 means your t goes away. And your plus 5, your last digit here, just goes away as well. So your answer is 15t squared plus 2. Now if you wanted to know the instantaneous velocity at some time, say perhaps at 1 second, then we would say that velocity, the instantaneous velocity at 1 second, would be 15 multiplied by 1 plus 2, or a value of 17 meters per second. And the unit of meters per second is our SI unit for velocity. Just wanted to make a special note, in doing this problem we did square the 1, and 1 squared is just 1. So we have a new function here. Our position as a function of time is equal to 3t to the 1/2. And so what is the instantaneous velocity? Well, first thing we need to do is take the derivative, or the dx over dt. And what we're going to do is bring the exponent of 1/2 to the front, so that'll be 1/2 multiplied by 3t. And the exponent to the t, or 1/2 minus 1, gives me a negative 1/2. Now we could rewrite this a little bit. This would be 3/2 t to the negative 1/2. Technically we could also write 3 over 2t to the 1/2. All right, let's do a little more in-depth example. And let's start with this position as a function of time. And I'd like to do a problem where first we have to find displacement. Now recall the symbol for displacement is delta x. And I'd like you to find the displacement using this function here between 0 to 1 seconds. Now if you recall, displacement is equal to your final position minus your initial position, or my position at 1 second minus my position at 0 seconds. And so what we want to do now is find out what is my position at 1 second and what is my position at 0 seconds. So my position at 1 second, we're just going to plug in 1 for t. And I get an answer of negative 2 meters. Now, what is my position at 0 seconds? That's going to be a negative 4 multiplied by 0 plus 2 times 0 squared. And that's just going to give me 0. So my displacement from 0 to 1 seconds is going to be negative 2 meters minus 0 meters. Gives me a value of negative 2 meters. Notice my answer for displacement is negative 2. So that negative indicates that my changes in position is 2 meters to the left or down, or in a negative direction from where we started. The next thing I'd like you to do is to find the average velocity in the x direction for this displacement of negative 2 meters in the time of 0 to 1 seconds. So recall, average velocity is your displacement over a change in time. In this case, my displacement between 0 to 1 seconds is negative 2 meters. And my time, which is 1 second, minus 0 seconds is just 1 second. So that gives me a negative 2 meters per second. Again, the negative is indicating a negative direction. So the average velocity in this time interval is negative 2 meters per second. Now what I'd like to do is find the instantaneous velocity at a time of 2.5 seconds, again using the same function. So let's write down that function again. So here is our position as a function of time. We want to go ahead and find the instantaneous velocity, so we need to take the derivative of this, which is going to be negative 4 plus 4t. Lastly, what we're going to do is plug in our 2.5 seconds in for t. My answer comes out to be positive 6 meters per second. Here's your practice. Have fun.